All right, so hi, my name is Adelbert Chang. I'm a software engineer at Box. I work on the search and analytics team there, where I do a bit of data mining and machine learning stuff. And today I wanted to talk to you guys about reasoning with types. Oftentimes when we think about a type system we work in, it can be easy to think about it as maybe just something the compiler needs to turn our source code into bytecode. Maybe it's something that may be helpful to just ensure the inputs to our function are sane. But we can actually do much more with it to help us not only write the software to guide us toward the implementation that we want, but also to formally prove certain properties of our programs. And throughout this talk, I'll be exploring some libraries from the type level project as examples of how we can use them to essentially apply how we can use types to reason about our programs. So here's how I envision sort of the next 40 minutes are going to go down. I'm going to first talk about some assumptions. Scala is a very flexible language. It allows us to write code in various different ways. So I'm going to lay down some ground rules about how we're going to approach our Scala development for the duration of this talk. Then I'll move into the first part of my talk, which will be on parametricity. The general idea here is how we can use parametric polymorphism, or what Java calls generics, to guess at what a function can and cannot do based solely on its type signature. Then I'll sort of switch gears a little bit and talk about logic and types, specifically how we can use the type system we work in and treat it as a sort of logical framework to formally prove properties about our programs, and how we can sort of encode proofs as programs. And then hopefully at the end, I'll have 5 to 10 minutes for Q&A. So some assumptions. For the duration of this talk, we will be subscribing to a thesis of functional programming. And what this means is a few things. First, our functions will be total. We will not be throwing exceptions anywhere. As long as the input is valid, as long as the input to a function is valid, that is, the types align, we will return some value back. Every single one of our inputs will relate to exactly one output, which means that if at any point in our program we call the same function with the exact same arguments, we should get the exact same value back. And finally, we'll require expressions in our program to be referentially transparent. And what this means is we can take any expression in our program, replace it with what the expression will eventually evaluate to, and not change the behavior of the program. All right? So parametricity. The idea of parametricity came about in 1989 in a paper called Theorems for Free, written by a famous computer scientist called Philip Wadler. And the general idea of the paper is types are documentation. Oftentimes when we think about documentation, we think about docstrings, right? Things like scaladoc. But docstrings can erode easily. As our function grows, as it changes, maybe even if the function gets deleted, the scaladoc can stay there. As far as the compiler is concerned, it more or less does not exist. It completely ignores it. So it's plausible to think that we change the spec of our function, or we change the type signature of our function, our scaladoc is out of date, and the compiler doesn't really care. Whereas if we use our types in a precise enough manner, hopefully as our function grows and changes, the compiler will catch us if we try to do something bad, or if we try to lie about the type signature. So types are something that the whole program has to go through in order for it to actually compile, and so it can't really erode as long as we use it in a precise enough manner. So as a demonstration of this, I have some examples. So first, we have a function here whose name suggests that it reverses a list. And it takes in a list of integers and returns a list of integers. And based on just the type signature, how many valid implementations are there for this? Well, certainly we can think it can return the identity of the list. It might return the empty list, or indeed actually return the reverse of the list. But by virtue of the fact that we know it's a list of integer, and we know how to manifest, say, 2 to 32 different kinds of integers, we can just manifest arbitrary terms of type list of int, right? So a valid implementation of this function, as far as the compiler is concerned, is we can completely ignore the input and just return a constant list of integers. Maybe we take the size of the input list and just wrap it up in a list. Maybe we dispatch on the size of the input list and then return a different constant list based on that, right? So we can do a bunch of weird things given just this type signature. So what can we do better? Well, when we reverse a list of int, we don't really care that we have a list of int, right? We just care that we have a list of something. I don't care what it is. As long as it's a list of something, I can reverse it. So we remove the idea of having an integer. So now what this function says is, give me a list of A. I don't care what kind of A, and I will return to you a list of A. Well, now we've removed the idea that we have a list of integer, and we no longer know how to just manifest arbitrary instances of A, right? The free theorem here now is any A that appears in the output list must have come from the input list. So our implementations are now restricted to, say, the empty list or some permutation of the input list. We can no longer just dispatch on a size of the list to return maybe a different constant list. We can't just ignore the input unless we return the empty list. So we've reduced our search space dramatically. Let's try a different example. What about reducing down a collection? Here, we're taking a list of ints, and we're producing an int. Certainly, the name suggests that we should be summing this list of ints, and the implementation here certainly does that. However, there are some problems with this, as before. We can still cheat with our knowledge of int, right? As far as the compiler is concerned, I can return any integer that I want, and it will be happy because I returned an int. Additionally, it's not quite generic enough, right? What if we wanted to sum a list of doubles or a list of longs or a list of big ints? We'd be writing effectively the exact same function for however many types that we want to do it. So being the good programmers that we are, we're going to abstract out this behavior. So we're going to solve the second problem first. I'm going to say, now, give me a list of A such that A conforms to this numeric type class, right? Numeric is this type class in the standard library that attempts to abstract over the behavior of all our numeric types. And here, I'm doing the exact same thing, except I'm just delegating to the 0 and the plus method in the numeric type class. And hopefully now, we've now made it more generic in that we can sum a list of long, list of big int, all with the exact same function. But have we solved the problem of knowing too much? Well, hopefully, we don't know enough to just manifest arbitrary instances of A, right? Hopefully, whatever A we eventually return is some function of the input. However, if you look in the numeric type class, we have this kind of strange method called fromInt that will take an int and is supposedly produce to you some value of t, right? That corresponds to that integer value. So we're now still able to manifest terms of type A using this numeric fromInt. So we haven't quite solved our problem yet. And additionally, it's not quite as generic as we'd like it to be, because you can imagine what if we wanted to reduce down a list of string, right? In the case of an empty list, we return the empty string. In the case of non-empty, we just concatenate all its strings together. Or a list of sets where we return the empty set in the case of an empty list, or we union all the sets together in the case of a non-empty list. So as before, let's think about what we actually need, right? When we reversed the function, we didn't really care we had a list of int. We cared that we had a list of something. The list was the important part. Here, what we actually care about is that we have a 0 value of type A for the case of an empty list, and to sort of act as the initial seed for our accumulation. And we need some binary operation to do the accumulator, right? So as it turns out, we have a notion of this, and this is captured in libraries like ScalaZ and Spire, which are part of the type level project, in this trait called a monoid, right? This is a type class that basically encompasses the idea of having some binary operation and some 0 value. An example of the monoid of int is simply to just add the two integers, and the 0 would just be the number 0. So we change our function, and we now say, give me a list of A such that A forms a monoid, and I will give to you an A. And now we've drastically reduced our search space again, right? No longer can we do anything like numeric fromInt. Anything we know about A sort of comes from the fact that it's a monoid. So the first argument to fold left says, give me some A to start with. And the best place to sort of get that A is monoid 0. And now the second argument to fold left says, give me a binary operation to do the accumulation. And indeed, we can get this from monoid append. So we've now not only made the function extremely generic in that we can now not only sum list of numeric types, but also list of strings, list of sets, even list of maps. We've also made our function so general that we've sort of been guided toward the implementation that we actually care about. We can go further, right? A lot of you might have heard of these things called functors, applicatives, and monads. I've written a function here that says, give me a list of A, a function from A to B, and a function from B to C, and I will get you a list of C. By virtue of the fact that we know we're returning a list of something, we can do some weird things, right? We can return just an empty list. We can do what we actually care about, where we map the composition of the two functions. Or we might reverse the list and then perform the map. And potentially other weird things. So let's look at the trait functor. Functor abstracts over sort of some context. And all you know about functor is that you can map over it, right? So if you have some f of A and a function A to B, it can get you an f of B. And now I modify my function not to say, give me a list of A and A to B and B to C. I say, give me some f such that f forms a functor and an f of A to B and an f from B to C, and I will get you an f of C. So now all we know about f is not that it's a list. By virtue of the fact that we knew it was a list, we could do some stuff with it. All we know about f is that we can map over it. So it's sort of the only reasonable thing to do here, and perhaps the only thing we can do here is to instead mapf.mapg, which is exactly what we want here. So parametricity is nice. With parametricity, we can write extremely generic functions, and we can also guide ourselves toward the implementation of a function and sort of rule out things a particular function can or cannot do based on solely its type signature. However, there is some sadness here. If we look at this function, I'm saying, give me an A, and I can produce to you a B. So for the past few examples, the only place we were able to produce an output is by some function of input. Here we're saying, I'm going to return to you a B. Well, I don't know anything about B, so hopefully you're giving me a B for me to sort of return or operate on to return to you. But you've given me an A, and as far as this function is concerned, there's no relationship between A and B. So if you see a function like this, you would expect it to simply not exist. It should not compile. But you can do some weird things by virtue of Scala being this very flexible language. You can do a senseless cast, do an as instance of, or you can completely subvert the type system and just simply throw an exception, right? As far as compiler is concerned, exception throwing is fine. And you can do other things that break parametricity, perhaps not in the context of this particular example, but in general, things like null, type casing and type casting. You can do side effects, and you can use methods on a Java-Lang object. Thankfully, for a lot of these things, in fact, I believe all of these things, we are able to, if not restrict ourselves from using them, but have the compiler stop us in the tracks if we try to use these. And there is a project in the type level project called wart remover, which is a compiler plugin that will essentially analyze the AST and make sure you're not doing any of these things. And if you are, essentially fails to compile or at least generate some warning for you. However, there is still one more implementation that is valid, and it looks like this. We simply recurse on itself. And as far as the compiler is concerned, this is fine, right? You're calling a function with the correct argument. That function returns a B, and you want to give a B back. So everything type checks, and it's fine. This, unfortunately, the compiler can't really catch for us, because to catch this problem is essentially to solve the halting problem. And as we know, halting problem is undecidable in the presence of Turing completeness. And Scala is a Turing complete language, so we're sort of stuck with not having complete totality checking. As a sort of fun fact, many theorem-proving languages or many dependently typed languages give up Turing completeness in favor of totality checking, because a lot of these theorem-proving languages are based around the fact of if your program type checks, you've essentially proved your theorem. And I'll get, this is sort of related to the second half of my talk. And if you were able to make something like this absurd function compile, then you've now basically broken the logical framework in which your theorem prover lives in. So they give Turing completeness to make sure that your functions do terminate. Before we leave the world of parametricity, let's go to a fancier example. So earlier I mentioned the idea of a monoid. And monoid is sort of a weird word. Some of you might be thinking that I just made up the idea of a monoid that just happened to suit my needs for this particular presentation. But actually, it comes from, it's a very well-defined idea, a very well-defined concept, and it comes from the wonderful field of abstract algebra. And there's many more cool things we can take from it, right? We have things with other weird names, like semi-groups, semi-rings, rings, and fields. And we can use these ideas in the same way that we used monoid earlier, to write not only very generic code, but to also ensure our implementation does not lie in regards to what our function can and cannot do. So we have this library called Spire that I mentioned earlier in type level that attempts to encode all these wonderful things. So for instance, a semigroup is just something that has a binary operation. We have a monoid that's basically a semigroup plus a zero value. We have a group that allows us to essentially not only add two things, but also subtract two things, and many other, and much more. So how can we use these things? Well, in my line of work where we do a lot of data mining and machine learning, dealing with vectors is a very common practice, right? We have various feature vectors. We want to do vector addition, vector subtraction, normalization, all this fancy linear algebra. So what sort of things do we do? As I mentioned, addition, subtraction, scalar multiplication. This is called a module. If you want scalar division, this is called a vector space. You can do normalization, and you can do dot products, right? These are pretty common linear algebra operations we expect to be able to do with vectors. Now, the naive way of doing things is to maybe just fix things, fix your modules as like a vector double, right? Vector here is the collection vector. double sort of encompasses anything we would really ever want to do with a number. We can add doubles, subtract them, divide, take the square root, take the factorial, whatever. Or maybe not factorial, but yeah. But just as before, why do we specialize to double? And in fact, why do we specialize to vector? We know a lot of things. We can do a lot of weird things to double. We can do a lot of weird things with vector. So what do we really care about? Again, this is going to be a common thing. What do we really care about when we work with modules and vector spaces? Well, we only care that we can add, subtract, and multiply the inner type, right, the scalar type. So put another way, we require the scalar type not that it's a double, but that it forms something called a ring. And here we have the definition for the ring type class. You can negate, which gives us the ability to subtract. We can plus, which is add, times for scalar multiplication. And now our module isn't fixed as a vector of double, but is parameterized over two types, v, which is the vector type, and r, which is the scalar type. And here, the implicit abstract def says we require our scalar type to form a ring. And now, given a module, we know how to add two modules together, subtract two modules together, and perform scalar multiplication. What if we want scalar division? That's something reasonable that we want to do. Rings support negation, addition, and multiplication, as demonstrated earlier, but not division. And to ask for division is to essentially ask for more power. So for example, integers are closed over the ring operations, right? If you take any two integers and you subtract or add or multiply them, you will definitely get an integer back. Whereas if you take two arbitrary integers and ask to divide them, you can't guarantee that the result you get back is an integer, right? If I took 2 divided by 4, that's a rational number, not an integer. So division is asking for more power. And the wonderful field of abstract algebra and encoded by Spire gives us the notion of a field. And a field is simply a ring, an addition with the ability to divide things. And now we have a vector space, which is basically a module that allows us to do scalar division. And we now require not that the scalar forms just a ring, but also that the scalar type forms a field. And as before, all of this type checks because if you have a field, you certainly have a ring. You just sort of ignore the fact that you can do division. At this point, I'm going to switch gears a little bit. That sort of ends the parametricity side of my talk. Now I'm going to talk about logic and types and how we can use type systems as a sort of logical framework to think about our programs. So there's a profound relationship between proofs and computation. For the next few minutes, for this part of the talk, I want to emphasize that we should not only look at the code as code we deal with every day, but also as a sort of thing that encodes a logical framework, encodes propositions, and a sort of mathematical proof. So this relationship is known as the Curry-Howard correspondence, or the Curry-Howard isomorphism. And essentially, it boils down to the more expressive your type system is, the more expressive the proof that your program corresponds to becomes. So an example of how this correspondence works, I put some in this table here. The very basic unit you have in logic is sort of a proposition, and that is simply just a type in our program. If you want to prove the proposition, you create a term of that type. So if your proposition is provable, it must have at least one term of that type. If you want to take the conjunction of two propositions, that is simply the type pair of P, Q, right? And you can think about how do we prove P and Q? How do we create a term of P and Q? We have to create a term of P that is to prove P, and we have to create a term of Q that is to prove Q. And then we have the famous modus ponens, which is if P then Q. And here that's just a function, give me a P, and I can reduce to you a Q, right? I have to prove P first. I'll give it to this function. This function will take my proof of P and then prove to me Q. So as an example, let's get the head of a list. I have a function that takes in a list of A and produces to me an A. Or we can think of this in the context of Curry-Howard and more specifically modus ponens. If you can prove to me a list of A, I can prove to you A. If list A, then A. Here, if I'm doing a pattern match, if I have an empty list, I'm simply going to just throw an exception. And if it's non-empty, I'm just going to return to you the head of the list, like you expected. The problem with this is that head is partial, right? Earlier, when I laid down the ground rules, we don't want to throw exceptions. Exceptions sort of subvert the type system, and by subverting the type system, you're subverting the logical framework in which your program lives in. So we don't want that. We want to return some value since nil is a valid input into our function. So OK, we'll return null. Null is a valid value as far as the compiler is concerned. Now the problem with this is null is evil. Let me convince you of this. Tony Hoare, who sort of invented null, calls null his $1 billion mistake. And the problem with null is that it inhabits every single type. So what this means in the context of Curry-Howard is that any proposition can be proved trivially, right? If a proposition can be proved, if a proposition is provable, there must be a term of that type. Null is a term of that type, so every proposition is provable. To actually prove it, we have to create a term of that type. As far as the compiler is concerned, null is a valid term of any type. So null essentially just destroys the nice logical framework in which our program lives in. What this means computationally is that developers are sort of left to their own devices to handle null, right? At any point in your program, if you have some sort of object, that object may or may not be null, and you're sort of left to doing null checks, and your code starts marching off the right side of your screen, and nobody wants to see that. And if at some point you screw up, the compiler doesn't really care, and at runtime you get a nice null pointer exception. So let's try again. Again, what are we really trying to do here? Well, here we're trying to say, if list of A, then A, right? Give me a list of A, and I can prove to you an A. Well, clearly, we can't quite do that, because if it's the empty list, then we have no A to give back. So what we're really trying to do is say, given a list of A, I may or may not be able to prove to you A. So we try to do that with null, but null, since it inhabits every single type, it's not exactly what we want. So we want some sort of type that encapsulates the idea of I may or may not have a value. And this should sound familiar to a lot of you. This is precisely option in Scala, right? So we either have none, which is an absence of a value, or we have some, which is the value that you care about. And if you can note that the number of inhabitants of option are precisely the number of inhabitants of A plus 1. And it's this plus 1 that gives us the I couldn't prove it part. So we rewrite our function. And we say, if list of A, then option of A, or give me a list of A, and I may or may not be able to prove to you A. And so when it's an empty list, I give you none. I wasn't able to prove it. If it's a non-empty list, then I was able to prove it, and here is the head of your list. However, at this point, a lot of people will say, well, I know my list will not be empty, right? Maybe they did, at the call site, they did a size check. If list.size is greater than or equal to 1, then call this head. Well, I got an option. I don't want to deal with it. I'm just going to call get on the option. Well, option get throws an exception, and now you're sort of back to where we started with just calling unsafe head on a list. So what do we do? Well, if you truly know your list will never be empty, you can think of that as saying, well, I have a proposition that says my list will not be empty. And Curry-Howard says, well, if you have a proposition, well, let's create a type that corresponds to that proposition. So we have a type called non-empty list, and this is actually available in the Scala Z library. And its constructor says, give me at least one element of A, and that's how it guarantees that your list is non-empty. And in the tail, you can just give me a plain list. And then now your head function says, if you can prove to me a non-empty list, if you can statically construct a non-empty list, statically prove that your list is not empty, then sure, I can prove to you A by simply giving you the head, right? Because we know by virtue of having a non-empty list, at construction, you had an A to give me. Now, the notion of a non-empty list is sort of weird, right? Maybe I concocted this just so I could prove a point here. But there are uses of this. In Scala Z, we have this notion of validation. And specifically, we have an alias called validation at null. At null is non-empty list. And you can think of validation as a sort of either, right? Validation is either successful or it fails, just like how either has left or right. The nice part about validation is that if you execute this validation against several inputs, it should be able to collect all your outputs. And if at any point one or more of your inputs fail, then it will collect any and all errors, right? Sort of with either or try, it sort of short circuits, it stops at the very first failure you give it. Validation is able to accumulate all these errors, and oftentimes you will accumulate these errors in the form of a list. By virtue of the fact that you know, at runtime you know you got a failure, by virtue of having a failure, you know that at least one thing went wrong. So if instead of non-empty list, we use list, well, I now have a failure of a list. I sort of know that the list is non-empty, but the semantics, the typed list doesn't encode the fact that I have a non-empty list, right? The list semantics say, give me any size list, whether it's empty or non-empty. So we provide non-empty lists. So when you have a failure of a non-empty list, indeed, you know by virtue of having a failure, there's at least one error. And the fact that you have a non-empty list of these error types proves that, yes, there was indeed one failure. Similarly, we have a function group by in the standard library that takes a list of A and then essentially sorts these A's by the function that you pass in. And it gives you a map from B to list of A in the standard library. Well, if you know that B exists, by virtue of B even existing in a map, you sort of know that the value corresponding to B is non-empty. Because for that B to exist, they had that function, this B was a result of some function result applied to one of the inputs. So list isn't quite what you want, since list can be empty, but you know sort of that it's non-empty. So instead, we could imagine a group by that returns a non-empty list instead. We can statically prove that by virtue of B being in this map, you have at least one element whose result when you pass it into a function is this B. So we're going to slightly switch gears a little bit, and we're going to talk about Curry-Howard and type classes. And this sort of ties back to the earlier sum function that we had. Given a list of A's, such that A forms a monoid, I can give you an A. Or put a different way, give me, if you can prove list of A and A forms a monoid, then I can prove to you A. Now, how do you prove that something A forms a monoid? What does it mean for A to form a monoid? Well, we're proposing the idea, to propose a notion of a monoid, we're essentially saying, well, we have a type monoid that has an append and a zero method. And to prove A is a monoid is to create a term of type monoid of A, right? So in a case where we want to prove that integer forms a monoid, we create a monoid of int. So our proposition is simply the type class monoid, and the proof of int is simply to implement monoid of int. And usually this proof will be like an implicit value inside an object, maybe the companion object of monoid. And one of the reasons you can think about why it's implicit is basically once we've proved it, we're sort of done. We don't want to pass around this proof all around our program, right? We've proved that int forms a monoid. The rest of the program should be able to say each time something expects a monoid, it should be able to find this proof. So in our sum function, when we call sum with, say, a list of integers, when the compiler goes to do the implicit search to look for something of monoid int, you can think of it as proof search. So in using Scala Z, if I just call sum of list of int with just the Scala Z monoid import, it will give you could not find implicit value. And you can sort of think of this as I couldn't find proof that int forms a monoid, right? There's no implicit value of monoid int in scope. So what do? We import the implicit value from a particular object. And now when we call sum with our list of int, what the compiler will do is say, OK, let's try to prove that int forms a monoid by looking for an implicit monoid int in scope. It finds the thing that we imported. We've proved if it's satisfied with the proof. And everything compiles and everything runs. We can go a bit further with the idea of a monoid. So many of the type classes and libraries such as Scala Z and Spire, right? Earlier I mentioned we had monoids, semigroups, rings, fields, functors. They are inspired by mathematics, right? Especially abstract algebra and group theory and category theory. And mathematics, as we all know, is very much governed by the idea of laws. So for instance, the notion of a monoid, we don't care just that it has a binary operation. We care that it has an associative binary operation. So the type classes that we derive from these things should abide by these laws. For example, monoids have an associative binary operation and a zero that is an identity in relation to this binary operation. And this is useful for two reasons. One is that it further restricts the behavior of the type, right? So this sort of aids parametricity, which is the first half of the talk. And it also allows us to exploit these laws. So for example, if you have some list of monoids, since you know it's associative, you can sort of partition this list into several chunks, fan it out to different machines or different cores, and then bring it all back and then merge them all using this associative binary operation. And you sort of know that this is sound because the operation is associative. Unfortunately, in the presence of a non-dependently typed type system, we can't statically enforce that an operation is associative. The compiler just checks that we took in two A's and produced an A, or that a zero is just some A. However, laws are perfect for what are called property-based testing, right? In traditional unit testing, we sort of feed in fixed inputs, and we say we expect this output out for these inputs. Whereas for properties-based testing, we're sort of asserting properties that the output will have for all inputs. And so for instance for a case of monoids, we say, well, for any three integers, the addition operation is associative. And for the zero case, for any integer, x plus 0 is the same as 0 plus x, which is the same as x. And when you run this test using a library like ScalaCheck and Discipline, again, libraries from the type level project, it will essentially just generate random values of integers, run it against monoid append and this monoid 0, and make sure that your properties hold. And so we sort of satisfy ourselves in saying, well, we ran a function for a bunch of random inputs, the property holds, let's just assume that we now have a valid monoid. So our code now becomes even more strictly specified by just the types and the properties, right? Our code was already fairly specified by virtue of using types, right? Using parametric polymorphism and thinking about our program in the context of Curry-Howard. Now, in addition with the properties that we assert, our program becomes even more strictly specified. So we're now moving away from the idea of, say, our unit test for the few inputs that we did for our unit test, this particular output was expected and it matches, or that our Scala doc says so. So in summary, types are robust. They're a form of documentation, and you shouldn't think of them as something just for the compiler. They're a tool for you to use to help you reason about your program, to help you implement your program. You should be able to use types to hint at what a function can do, but perhaps more importantly, what a function cannot do. Types are a static property of your program in that if you try to subvert the type system, you've now introduced not only an escape hatch in your program, but also a logical inconsistency of your program in the context of Curry-Howard. And in general, the general theme is recognize the difference between trust me, I'm a nice person, I will or will not do this, and the compiler would not have compiled or would only have compiled it if it did or did not do this. That's it. Any questions? So one example off the top of my head right now would be in our sum example, the only reason the sum function worked the way it did was because the identity was related to the binary operation. If I used 0 as like 1, as the integer 1 instead, the sum function wouldn't have really been a sum. Same thing with like set union. If instead of the empty set, I return like some arbitrary set as a 0, that's not really set union. So that's one case off the top of my head. Up here, I can't really think clearly, so maybe, yeah, in the hallway, we can talk.
So, somewhat related to get to the 0 thing, in your sum function, what prevents you from simply returning the 0 of your monoid instead of summing?
Right, so there's nothing, as far as the compiler is concerned, there's nothing preventing you from 0. The idea here is the goal isn't exactly to just say we have only one valid implementation of this function. The general idea is how we can narrow down the search space for our implementation, right? If we use numeric, we could have done a lot of weird things with numeric by virtue of using from int, whereas here we have a more limited subset of things we can do with the function. But yes, if we just return monoid 0, as far as the compiler is concerned, everything is fine. But if we use something like Scala check or discipline, use property-based testing, we can gain more confidence not only from the types, but also from the property that we specify.
Can you give some more examples of how you're using these things that you described to the benefit of your machine learning programs? Like that example that you gave that you use a property of the monoid to distribute computation amongst multiple cores. Are you doing more things like that?
In terms of machine learning, I know there's this really interesting project, at least, so it's not something that we use directly, but something I'm sort of looking into. There's this really interesting project in Haskell called HLearn, where they basically exploit the monoid properties of certain machine learning algorithms. And what they're able to do with this is you can write a particular workflow, and then you can run it sequentially on one CPU. And once you wanted to distribute it to several machines or something, it's able to do that extremely easily and sort of in a free way, because by virtue of it being a monoid, it can run it serially if it wants to, but it can also fan out to several machines. At Box, the way we do machine learning is all our vector types that we're dealing with aren't just monoids. We do the whole ring field thing that we described about. And this has helped a lot of people, even those who aren't as familiar with Scala, it helps them write the correct implementation that they intend to, because by virtue of the fact that they only know that the scalar forms like a field, they can't do weird things like, oh, if this thing does not equal 0 or something like that. All they can do with it is the operation specified on this particular field. Thank you.